Hi everybody, today we're looking at figurative numbers and how they apply to arithmetic sequences and series. So here we go. So first thing we need to do is to consider the following pattern. 1, 2, 3, 4, 5, and it goes up 1, 2, 3, 4, 5, and this is going to form the base of all of our patterns. The first pattern we're going to look at are triangular numbers, and it should be quite obvious because they are making triangular shapes. So the first one would be 1, and the first triangular shape has 3 dots, the second has 6 dots, 10 dots, and then 15 dots. They're called figurative numbers because they make figures. Now, square numbers are similar. 1, 4, 9 making a square, 16 making a square, 25 making a square. We can even do pentagonal numbers, where we start with a really small pentagon, an infinitely small one, and then we go up to 5, our normal looking pentagon, and then we have that shape here, and then we extend it another lot, so we have now 3 on each side. Then we go to 4 on each side, remembering that we still have the internal ones, and then you have this really crooked 5th one that I didn't draw very well, but you get the idea. So 1 dot, 5 dots, 12 dots, 22 dots, 35 dots. Now, if we're looking at arithmetic sequences, we do have an arithmetic sequence here. It starts with 1 and it goes up by 1 each time. We can see that the difference is 1. So we could do Tn equals a plus integ 1d, where a is 1 and d is 1. Then we could simplify that and we'd get from n the value of each term. That's pretty simple. But when we look at triangular numbers, we can see the difference is no longer constant. But if I put in another one here and continue the pattern backwards, I can see here that I have a sequence increasing by 1 each time, which would make it arithmetic. And if I add these numbers up, I get the term in the triangular series. So 1 plus 2 would be 3, 1 plus 2 plus 3 would be 6, plus 2 plus 3 plus 4 would be 10, and so on and so forth. So it's like the term number is equal to the sum of the differences, where the first one is 1 and it's increasing by 1. When we look at the square numbers, the term number is relatively easy to find. It's just n squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, so on and so forth. But we could do something similar than what we did with the triangular numbers. We could say Tn equals Sn, and if we have 3, 5, 7, 9, if we put 0, 0 in, that would give us 1. This is an arithmetic sequence increasing by 2. A would be 1, D would be 2. And the same thing happens with the pentagonal numbers. 0, 0, 1, 4, 7, 10, 13. Tn equals Sn, A equals 1, D equals 3. There we go. So now we're going to have a look and see what that looks like when we have a look at the different formulas. So for counting numbers, we found out that T1 was 1, D was 1, Tn just equals n, and that's wholly consistent with our first set of numbers. Then if we have a look at triangular numbers, where A was 1 and D was 1, we look at the sums rather than the term. We use the formula that we had in the past. Looks like this is missing a bracket. We'll end up with half n squared plus half n. For square numbers, we know that it's going to be n squared, so I'm not going to simplify that one. And here I did it for T3. So for the third number in the series, we find half of the first term, which would be half of n. Half of n, which is half of 3, times by 2 times the first term, 2 times 1, plus n take 1, which would be 2 times 3. That'll give us 3 on 2 times 8. which is 24 on 2 or 12. And if we have a look, the third term is indeed 12. So if we simplify that down for n, we'll end up with half n squared plus half n, and we can now work out any number in the triangular series without having to do complicated formula. Oops, not for triangle. For pentagonal numbers without having to do either millions of pictures or lots of different formula. Now that's enough knowledge for you to attempt the AMC questions. You may need a little bit of extra algebra to do some of the questions. So a plus b all squared is equal to a squared plus 2ab plus b squared, and n plus 1 all squared is n squared plus 2n plus 1. So there you go. That's the last video in this series. So hopefully I'll see you in the next one. Thank you, everybody.